time they keep raising the bar, so I wonder the next one. So, when Arunanshu joined, we have sort of prodded us to work on a device I had no idea how to do. Spinware. So, we joined hands with Dimitri, who is on listening to us. And most of the work Arunanshu did, at least in the SpinFed part, was either on his own or by collaborating with others, because my knowledge was quite small in the area. Now through him, I think I have developed some knowledge. And in the meantime, we got involved in other very interesting topics. Now, having said all that done, there's a competition between him and his recently married wife, Sita, who finishes PhD later so they can stay a little longer on Stanford campus. She went to Harvard as a faculty member in the math department. But in case Arunanshu can't find a job as an engineer or a teacher or something, I just found out a few days back he is a very accomplished singer. He can support himself, both Western music and Indian music,
Thank you so much. Thank you for the kind introduction. And I'm very excited today to talk about the work I've done at Stanford, as we're talking about tunneling contacts and spin transport. And as we know, in the last 30 years, we've seen an exponential improvement in the computational power that's available to us. And the main driving force behind this has been the shrinking of transistors to smaller and smaller dimensions. And as we continue to do this, we're now reaching a point where shrinking them any further is not only difficult, but also the physical effects that start showing up at these length scales put us in a situation where we no longer can meet the demands of Moore's law by simply shrinking these devices further. And people have come up with many innovative solutions to this problem. One of them is using new materials like germanium or 3-5 semiconductors, which are high mobility materials. They help us make faster transistors. Another more radical idea has been to use different state variables, like using electron spin information in addition to electron charge information. And at the same time, there's been a continuous scaling of memory devices also. And people have suggested new device ideas like phase change memory and magnetic RAM to keep up with the demands of Moore's law and continuous scaling. And in my talk today, I'll be talking about 3 kinds of devices which exemplify some of these ideas of new materials, state variables, and also a new kind of memory device. The first of them is called the metal insulator semiconductor contact, or the MIS contact. So consider the MOSFET. In essence, it's a gate-controlled switch, which in the on state has a very low resistance, and in the off state has a large resistance. And a better MOSFET is one in which you can have a lower on-state resistance and a higher off-state resistance. And this resistance in a very simple model can be thought of as a contact resistance, a channel resistance, and another contact resistance at the drain end. And while we've moved to high mobility materials like germanium, and we've tried to reduce this channel resistance, contact resistance is a major problem when it comes to germanium, especially n-type germanium. And a typical contact to n-type germanium gives us contact resistances of about 10 to the minus 4 ohm centimeter square, whereas a good transistor would need at least 10 to the minus 7 or below. And in order to solve this problem, a very interesting solution was proposed by Dan Connelly and co-workers. And they suggested that by insertion of a very thin insulator layer at the metal semiconductor interface, we can reduce the contact resistance over there. And in our work on this particular kind of device, we studied very important issues related to this structure. We first calculated what the minimum contact resistance achievable by such a technique is. We then explored the choice of interface materials for this device. And finally, we've also studied some of the mechanisms which are responsible for contact resistance in this case. The second device that I'll be talking about today is very similar in structure to this device again, except you now replace the metal source and drain electrodes with ferromagnetic metals. And what this does is that in addition to having gate control on your transistor, you can also control it from the relative orientation of your source and your drain ferromagnet. So if you have them in the parallel configuration where they both are magnetized in the same direction, you have a low resistance state. And in the anti-parallel configuration, this device has a higher resistance state. And the interesting spintronic effects which are in operation in this device is the injection of spin polarized electrons from the ferromagnet to the semiconductor, the transport of these spin polarized electrons across the channel, and finally the detection of spin polarized electrons at the drain end. And this additional control knob of having magnetization in addition to gate control on the device enables many interesting device concepts, such as having a very low off-state leakage so that you have a low leakage transistor. You can think of this device as a memory element integrated into the transistor. And at the same time, there's also some ideas on how this idea can be used to make reconfigurable circuits. In our work on this particular device, we've studied the semiconductor spin transport problem and developed a very efficient formalism to study semiconductor spin transport. We've modeled the properties of spin injection and spin detection at these electrodes. And finally, we put all these together to do the first simulation of a spin MOSFET in this drift diffusion regime. The third device that I'll be talking about then, after this, is again very similar to this device in concepts of operation, except it's a memory device. And this device is called the magnetic tunnel junction. Once again, it consists of two ferromagnetic electrodes sandwiching a very thin tunneling barrier. And you can have a low resistance state in the parallel configuration by magnetizing the electrodes in the same direction, or a high resistance state in the anti-parallel configuration. And this device is extremely promising, shows a lot of commercial promise also, because it has a high speed, it's a low power device, it's non-volatile, and also extremely scalable. And one of the major breakthroughs in this particular device has been the introduction of the magnesium oxide tunneling barriers. The magnesium oxide tunneling barrier is extremely special because you can make a fully crystalline stack of iron, magnesium oxide iron, and that means that these devices cannot be studied with approximate models anymore. You really need to understand the atomistic structure and electronic structure in this device. And in order to do that, we've developed an extended Huckel theory-based simulator to study the electronic structure. And using this, we've also studied the effects of Fermi-level thinning in this device and the use of alloy electrodes in such a device. So here's the outline of my talk then. I'll talk about these three devices that I just mentioned, and I'll end with some contributions and acknowledgements. So let's start with the MIS contacts then. So as we just discussed, the germanium transistor has the problem of having a large contact resistance. And the reason for this large contact resistance is called the Fermi-level thinning effect. In an ideal device, you can imagine that with a low work function metal, you would have a very small Schottky value, and you could have a low contact resistance in your device. However, it's been experimentally observed that independent of the metal work function that you use, the Fermi level of the metal always spins near the valence band of germanium, so close to the germanium valence band. And this gives rise to a very large Schottky value at the interface, and this leads to a large contact resistance. The extent of this Fermi level pinning problem is determined by a pinning parameter S. And the pinning parameter is defined such that S equals 1 indicates an unpinned contact, where you can modulate this Schottky barrier very well by changing the metal Fermi, the metal work function pi n. Whereas a pinned contact, which is closer to the case of germanium, is one in which you cannot easily affect the barrier height by changing the metal work function. So Dan Connelly and his co-workers proposed this very interesting solution that by insertion of a very thin insulator layer between that metal and semiconductor, you can reduce the Schottky barrier and hence reduce the contact resistance. And if you look at a typical plot of the contact resistance